Hi guys, in this lesson we are going to learn how to calculate the time and space complexity of different functions. We'll look at some typical examples that will help you understand how to analyze performance in real code. Time complexity helps us estimate how much longer a function will take to run as the input gets bigger. Space complexity tells us how much memory a function uses as the input size grows. So let's get started. Here we have this little function. As you may see, there is just one number and one expression with no loop, so n equal 1. So f of n is equal to 1. So big O of 1 for the times complexity and big O of 1 for the space complexity. Big O notation is used to describe the upper bound of a function's time or space complexity as the input size increases. So this is a very simple example. It doesn't help so much to understand, so let's see something more complex. In this function there is a loop. So n in this case of the time complexity is equal to the length of the list. So f of n it's equal n. So the big O notation is big O parenthesis n for the time complexity, and it's again 1 for the space complexity. Now I want to point out something. Let's add items dot extend parenthesis items. If the list items was double the size, would that change the time complexity? The answer is no. You might think the function becomes 2n, but big O notation only cares about the rate of growth. Constants are dropped, so it remains big O of n, also in this case. Now let's see another example, again another loop. So again n is equal to length of items, but there is a small difference in the space complexity. So f of n it's equal to n, so big O it's n again for the times complexity, but in this case is also big O of n for the space complexity. Because as you can see, here we append item by item till the end of items, so the big O notation is n also for the space complexity. Nothing else to say about this. Here we have a nested loop, which is a bit more complex. Let's analyze one by one. So n equal length of items. Let's say this. And then there is n1, which is the first loop. Let's name it n1 and n2. n1 equals to n, okay? n2 equal n divided by 2. That's because n2 is a bit different. It starts at I plus 1 and goes to the end, so it runs about n divided by 2 times. F of n it's equal to n1 multiplied by n2, which is equal to n squared divided by 2. So what is the big O notation? N squared. So, big O of n squared for the time complexity, and O of 1 for the space complexity. We are not occupying any space. Now let's look at this next function. Here we check if a number is a perfect square using a loop. We go through values of k such that k multiplied by k has to be smaller or equal of n. So how many times do we loop? Well, if n equal 1, which is equal to 1 squared, then n equal 4, which is 2 squared. Then n is equal to 9, which is 3 squared. And so on. As you can see, the pattern is n equal k squared. So, square root of n is equal of k, which means that the big O is square root of n for the times complexity, and again 1 for the space complexity. Big O 1 space. Now let's take a look to the last example. In this case, n is divided by 2 until it's equal to 1. So n divided by 2 equal n divided by 2 raised to the power of 1, and n divided by 4 equal n divided by 2 raised to the power of 2. Then n divided by 8 it's equal to n divided by 2 raised to the power of 3. And so on. Again, the pattern it's n divided by 2 raised to the power of k, which, as we said, we stop when n divided by 2 raised to the power of k equal to 1. So n equal 2 raised by k, which is equal to log of n equal to log of 2 raised by k, which is log of n in base 2 equal to k, which means that big O parenthesis log of n for the time complexity, and again big O of 1 for the space complexity. Let's recap. Lesson 27 algorithm. We learned how to measure time complexity and space complexity, and how to express this using big O notation. So for this lesson, that's enough. Thanks for watching, and see you in the next lesson.